All right, so today we're going to tackle a few lead code problems. We're gonna try to do at least three today, maybe four. But I'll start with an easy one, and then I'll go with the medium one, and then we'll see if the third one will be easy or medium. But yeah, let's go ahead and start. So let's see. Um, okay. Given a string s containing just the characters parentheses in curly braces, determine if the input string is valid. Given a string s containing just the characters, the input string is valid. And input string is valid if open brackets must be closed by the same type of brackets. Open brackets must be closed in the correct order. Every closed bracket has a corresponding open bracket of the same type. Closed bracket is okay. Okay. So I'm guessing there will be a lot of string manipulation here. Let's see. So you could do um, uh, um, all right, so you could do let's see. You could iterate through the string and look at each character and then determine if there's anything missing or there's anything wrong. So you could determine, like, you take the string, you iterate through it, and then here's the characters. Okay. So you iterate through the string, you look at the first parentheses or bracket, and then you determine what is the next thing that you need to look for. If for it to be a valid or invalid string. And if the next character is not what you're supposed to get, then it becomes invalid, basically. So I'm thinking we could do something like let next, and that could be null. And next will be like the next character that we are expecting. Or mm, um, or wrong wrong character. So if you could do like a for loop, and then inside the for loop you'd have the string. So I is smaller or smaller than the length of the string, and then it's gonna go, and then you add one to the string, and then you have to look at I mean I think I know it. I mean, that's what I have right now in my as a solution. That's what I can think of right now. So let's say you have an array of brackets. So you have an array of all the open brackets, I guess, and then so all of these. Let closed, and then, oops, did I submit it? No. Let open would be equal to another array with the closed. It's actually the opposite here. Closed, and then here you have closed and closed. And so basically what you'll do is you look through the string, and if wait, so it has to be closed. Open brackets would be closed by the same type of brackets, right? Open brackets would be closed in the correct order, right? So every closed bracket has the same type. Wait. So let's say the string starts with a parentheses, open parentheses, this. The only valid character that could come next are any other open bracket or parentheses, or the corresponding closed bracket right after. Because if you get a closed bracket of any other kind, the string becomes invalid because it's not closing in the right order, and it creates problems. So closed bracket screens are the same type. Every closed bracket screens open bracket of the same type. So with this logic, you would check for these two. Same type of bracket must be closed in correct order. No, it doesn't work. It doesn't work because after you get this, let's say, let's see. Let's say you get this, right? That works up until now. My logic works, but now anything could work here. An open of any kind and a closed. No, not a closed of any kind. An open of any kind. An open of any kind. But a certain type of closed. A certain type of closed. So So let's see. I guess we could do like, you check the string up until that point, right? Up until here. And then you say, okay, so if you're at a closed bracket and everything is worked fine just to that up to that point, right? So that could be this, or it could be this, or it could be this, right? Anything after you get to a point where something has closed and the string to that point, up to that point, is valid, what you need to do is the next character could be any open bracket or parentheses. Only any open or any closed that has already been recorded before. So let's say you could do a map, right, of everything that's been recorded so far in the string, and then see if what comes after that makes sense. So let's see. So do I need those two arrays is the question now. So you get open parentheses. So when it's open, right? Wait. When it's open, you can get any open or, any open or corresponding closed. Corresponding closed. Corresponding closed. Corresponding closed. From current string. So far, I guess you wanna. And if it's closed, open corresponding, right? So here, the only thing that would make sense would be a closed bracket, if it's closed. But anything open could work. So basically and here, only one works, right? So the last open, right? Okay. So here it could be when it's closed, right? When it's closed, it could be any open, right? It could be any open or corresponding closed. So it's always that. Really. Corresponding closed. So any open or corresponding closed. So you'd have to calculate what the next corresponding closed would have to be, which would be the last So wait, here any open, corresponding closed, and here it's any open corresponding closed, corresponding closed, corresponding closed. Corresponding closed. So the next, okay, so here any open and corresponding closed, which is the last open that hasn't been closed, right? And here it's the same thing, the last open that hasn't been closed. Okay, so next, let next closed would be the next one that needs the next closed bracket or parentheses that would correspond with what has happened before in the string. But now, how do you calculate that? Is a good question. So you could create a map and record the amount of closed or open of each type, right? But that doesn't necessarily give you the doesn't necessarily give you the doesn't necessarily give you the order, because here the only corresponding closed bracket or parentheses that would work would be a square bracket, because the last open was a square bracket, and here it would be a square bracket again, because the last open that hasn't been closed yet is a square bracket. So I feel like I'm close to the solution here, but let's see. Okay, so closed. So you have to figure out a way to record or calculate the next closed bracket that will work. And that would be the corresponding bracket that hasn't been the last open bracket that hasn't been closed. So we could create let's ignore the open and closed arrays for now, but I'm not going to delete them because maybe I'll use them, I'm not sure yet. But we could create a current string, right? That will essentially be the string up to the index that we're in here. And so let's see, close. Got to think here. So you could create like an array, a map. Oh wait, I think I know. So you'd have to put in. You'd create a map, right? A map. Oh my goodness, a map. I have an idea, but it would be in O of n squared. I'm trying to do it in O of n or less. But O of n squared, I would simply do like create an array with everything that's been recorded so far and figure out which of the past open brackets that haven't been closed is closer to the current index, and that would be the type of bracket that could be allowed. That could be allowed for the next closing bracket. I don't know if that makes sense to you, but it does to me. However, that would make, as I said, O of n squared. And I need something that is more efficient than that. So let's think. So we have we could use a map. We could use an array that would work. Would it work? An array with the ones that are it's like I can't even think, bro. String map. What? I need to find the last open bracket that hasn't been closed. How do I do that? That's the question. That's the question. That's the question here. Corresponding. Yeah, I mean. Yeah. So, it says here stack. So maybe I should use a stack, which is oh wait a second. Wait a second here. No, that works. Wait. So eliminate that. Oh, I know. Okay, I think I know. I think I know. Okay, so basically you create a stack and it records current. So you create a stack, right? And the stack will record every bracket that comes in from the string that is given in the parameters. And so basically if the stack records only open brackets, right, all the way to, it's only open brackets, it'll keep stacking everything. As soon as you have a closed bracket, if it's the right bracket for what has been for the last open one, then it will delete the last two elements in that stack. And then you do the same process with the next character, which could be open again or closed. If it's closed, then it has to correspond to the last element in the stack. And if it's open, then you keep doing the process. You keep stacking them, and then as soon as you get a closed one, you check if it's corresponding to the last open one, and if it is, you delete both of them. So let's say you get an open one here. All you do is you delete that one in the stack, and you get back to only opens. And if it's a closed one, it's not the right one, then you know the string is not valid, and you return string invalid, right? Okay, so that makes sense. I don't think I'm missing anything here. So basically, the stack will be current. It will be an empty string. And so if the first string, let's see. So the first element cannot be closed. It just can't be a closed bracket. It has to be open. So let's see. So you could start the stack with a simple you do S1 as 0, which would be the first if current or if closed includes current, then return false, because the first element in the string cannot be closed. It has to be open. Okay, so if that's not the case, we can go through the loop and then look at the next. We can start at 1 here. 1. So here we look at if if closed. Wait, what are we looking at? We're looking at the next one needs to be open. If it's open, we include it in this tag. So if open includes now I'm not sure if I don't even think you need to do this, like put these here. I think that's good enough. I'm pretty sure that's good enough. Anyway, we'll find out. Return, no, not return. You do current plus SI, I think. pretty sure that's what it is, right? And then if it's open, right? It is if it's open. If it's not open, then it's closed. And then you could do this and put a continue one. Where's the no? It's supposed to be inside. Like that. Oops. And if it's not open, then we know it's closed. And in that case, we need to check that it's. Wait. Okay, we're gonna get into some problems later on, but for now we're good. So here it would be closed. So in that case, you have to make sure that the closed bracket is the same type as the last open. The closed bracket is the same type as the last open, right? Open. Okay, so you have to see if SI is equal to okay, so that'll be a bit. So SI, so here it's closed. So I'll put a note here. Closed. Open. And here, well, here it's closed. So here, if I is equal to index of. So I closed equal to closed index of close index of closed. So basically we're trying to check if index of, no, it's not. That's not what it is. It's supposed to be we have to check open, closed, if it's the same type. SI. Closed. Okay, I get it. Wait. Yeah, I get it. So open. Right, open. So you have to, don't know how to explain it put it into words, but open index of the last element in the stack, which would be last index of, right? No. How do you check the last element of an array? So you do like, I don't know how do you do that, bro. Last, I know for sure there's a way to do this. So if you look at these methods, right, they are perhaps last index of, search, match, match all, search, maybe search, ends with, includes, character, add, code, split, pad, start, trim, end, substring, slice, to locate, concat, no, pop, shift, push, unshift. I think pop is the one. Or match. Slice. Extracted. Slice. Extracts a section of a string and returns it as a new string without modifying the original string. Lazy. So from the oh yeah, I remember now. Removes it. Extract section of a string. Index start, index end. One, two, yeah. -1. -0. That's probably not a -1. Yeah, slice. So you'd have to check. Okay, so open. Wait. Index of closed. Index of stack. Well, the current slice -1. And then that will give you the type. Index of. So if that's not the case, then wait, closed. Yeah, that should work. And then if that's not the case, it means that no, if that's the case, it means that the new closed tag corresponds to the last open one. Hence, you can remove the last pair of closed in current. The last pair of closed in current, exactly. So basically you do pop on current, I think. Wait. Gotta think here. So, right, that's it. You just remove the last element in current. And you can do that with pop, I believe. Let me double check because I'm not sure. I should probably know them by heart. Method removes the last element from the array and returns the element. This mentions the length of the array. Okay. Perfect. So that's what it does. It removes the last one. And so in that case, if the string is, if S is this, here, current would be empty, basically. It would be. Because like if you have, you have a string, right? You have this. What does why? Why is that? It doesn't work on strings, obviously. But what you can do is you do can you do, you just have to do this? No, I don't think so. Okay. Well, you can do let array is equal to array from, something like that, from plants, something like that, I think, I'm not sure. And then array does that work? Do I need to do this? Plants. Yeah, okay, you have to do this. Pop, and then here, do this. Okay, so you have to do array from to convert the string into an actual array. And then so here it's supposed to be an actual array, not a string. An actual array. And then you have to do push, not this. You have to do, no, push or what? Is it push? No. Or unshift. Is it push or unshift? I can't remember. It has to be added at the end of the array. So it would be, if I remember correctly, it would be shift. No, not shift. Push. It would be push. Yeah, it would be push, I'm pretty sure. I'm pretty sure it would be push. Adds one or more elements to the end of the array. Exactly. And unshift is to the start, to the beginning, exactly. So it's push that we need. We need push. And then, exactly. So here you move the last element. And if that's not the case, then you do you add? Wait, if that's not the case, then the array is invalid. The string is invalid, right? I'm pretty sure that's what it is, right? Right, that's what it is. Because to that, after this, everything here is dealing with else return false. I'm curious to see if I could write it differently, like this, continue. And here you do return false. Would that work? I'm not sure. So now that makes sense to me. Not sure if that would work, but it makes sense to me. Right? Let's try it just for fun. Doesn't work. True. Right. There's no way to return true now. If it's closed, blah blah blah. Else, I think I have to do else return false. I spent way too much time on this problem for sure. Way too much. Way too much. Return false. And then return false. And then after all of that, if nothing happens, you just return true. Does that work? It doesn't work. So I clearly have an issue here. This is wait. Okay. So it's returning false here. If si is equal to this, maybe. Includes current, no, current, this, that'll, current, includes current. There's something here that I'm completely missing for some reason. Open includes si. Includes si. Open. Yeah, there's something here I'm missing. Not sure what it is. Includes. Yeah, you add that to the array. Continue. Or break. No, you just continue. If si is equal to closed index of slice, the last one, right? does that give you no, that should work. Open index of open key the same index close. Yeah, I don't see what's going on. I don't see what's wrong here. Current pop. Continue. Else return false. So I'm pretty sure it's probably here. Something's going on here. Not sure what it is. Let's find out. So is valid. Nums is supposed to be something else. It's supposed to be S. Here S. And here is supposed to be a string, right? A string with this. Give you false. Okay, so why is it false? If close includes current 0, so it's just like try to figure out what's going on. False. Okay. It does not include. Right. It does not include that. Is this false? Console log this false. Is that actually false? Open includes no. Yes. No. 1 is supposed to no, it is false. It is false. It is false. Okay. Now this is really this is supposed to be true. No, it's not. No, yes, it is supposed to be true. But it's giving us false. So let's see. So it's giving us this guy, right? Which makes sense. And then this is supposed to give us what? Supposed to give us, it's giving us undefined. Okay, so that's the problem. So maybe this needs to be a string. Perhaps index of current size. Wait. We have a problem here. No. Index of this. Does that give us something? Console log current index of this is 0. Okay. So this is supposed to give us this. Correct? Yes. Oh, I see. Okay, so it returns an array. Slice returns an array. I didn't think it would return an array. I don't think that's what they. Is that actually what they did? Yeah, it has to return an array. Makes sense. Jeez. Slice. Yes, it returns an array. It returns an array. Is it pop? Yes, it's pop that returns the actual element. So it has to be slice. It has to be slice and then 0 because it's only 1, and then it's true, right? Exactly. Okay, so that's just not me. That's just me not knowing how slice works, basically. But now that should work. Okay, so submit. Doesn't work. So if it's only one bracket, it has to contain all. Wait a sec. Yeah, I didn't consider this thing here. So yeah, I should have checked before. But the closing, if it's only one open bracket, then it has to be false. False. Length. If it's only one, then return false. So I guess I could put it here. Or s length is smaller than 2. If that's the case, then return false. Right? Every closed bracket has a corresponding open bracket of the same type. I think that works. No, because we have a problem here. Because if this is something like this, and the last one is open, we might get a problem. So let's see. Here, I add this, and now, and now it'll return true, but it's not true because this guy needs to, so essentially the current at the end needs to be empty. The current array, the stack needs to be empty, right? So if current length is length is essentially 0, then if it's not 0, then return false. Basically, so now it's false, right? And I think with that, we get all the possible outcomes, and it should work now. If not, then I don't know. Okay, so it does work. That was more complicated than I expected, but yeah, it took me way too long. It took me an hour to do this, and it should have taken me 15 minutes. So yeah. I'll have to speed it up, man. The next time I'll have to speed it up and solve these a lot more quickly. Valid parentheses. I just need the solution, buddy. Because I think that my solution is not horrible, but I'm pretty sure there's a more simple way to do this. And I completely overlooked it. There probably is a much more simple way to do this. Yeah, I think that I probably overcomplicated this. Yeah, there you go. So here you get the stack. The sort of closing brackets expected. The closing brackets expected. Okay. Traverse each character in the input string for index and blah blah. So if open parentheses are present, push it to the stack. Okay. Okay, so it's kind of similar to what I did, but not really. I overcomplicated my solution for sure. Else if stack dot pop isn't equal to, wait, if a closed bracket is found, check that it matches the last stored open bracket. Oh, I see. Wait a second. So you have stack pop is index. So you have the stack that records is it close? Okay, yeah. It's check that it's matched the last store open bracket. Pop, stack pop. Yes, so that's basically what I did, but if stack length turn false. If it's stack length, wait, what? Okay, makes sense. Wow. Yeah, makes sense. Because if it's 0, it's false. If it's not 0, then it's true. Wow. That's a very clean way to do this. Very, very clean way. And it's annoying that I didn't found that solution. Although mine works, it's just overcomplicated for no reason. But yeah, I mean, that's a very cleaner, purer way to think about the problem. And mine is, I mean, the concept is still there. The concept of the stack is still there, so I wasn't completely in a different world. Yeah, so I was on the right track, but I overcomplicated things. Yeah, I mean, yeah. But what if, what if the first one is, yeah. I mean, this really shows a very good understanding of the methods and the push pops and all that and the stacks. But yeah. I should probably write it out just to make sure that I store it in my brain. It's essentially what I did, just in a much more complicated way. Close Yeah, I mean it's the same thing. It's exactly the same thing. Stack pop. Yeah. I mean, like this could be here, and the last open, the last closed, closed. Yeah. Yep. Pop. Yeah. I'll write it. I'll write it out because it'll probably stay in my brain after. So function is valid. So he created a stack, right? Right. Even cleaner way to do this is using switch. I'll do it using switch. For so stack. So let stack equal empty array. Empty array. So 4 is equal to 0. Obviously, put s as length. And here you could do a switch, right? Switch, which means that it'll check for. So here you'd have I, and then here you'd have case 1 or something like that. Case, which is, I don't know what the syntax is of switch. Switch JavaScript. Can't remember what it is. Yeah, okay. 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 So you do switch and case. Case if. So we're looking at open brackets. So if it's open, curly, then you do stack, push, closed, curly bracket. Curly brace or curly bracket, I don't know. And then case open square means you stack, push, open square bracket. And then case open parentheses, you why do I write it like that? Push open. And then default is wait, I can't remember what the break is. break statement is counted. After the first close with a matching value. No. I don't see how the break is useful. You can use the break statement within a switch statement body to break out early, often when all statements between two case clauses have been executed at first. Clauses. Okay. Oh, we don't need the break, but we can do default, which would be you still do the thing. Default would be if s I is not, so if we get to default, then it means that the element is a closed bracket, and if it's not equal to the last open bracket or the last corresponding closed bracket in the stack, then you return false. And then and that's it. And then after the for loop, return stack.length. That's it, right? That's not it. What am I missing? I don't see what I'm missing here. True. So here it's returning true, so it's false. What? No, it's returning false. So this is, so the length is greater than 0. However, it shouldn't be greater than 0. Thing is, console log stack returns false. That should be true. If stack, right? And what is S? Oh, do I need to do a break? I think I need to do a break here, because it'll always, wait, no, default, no, is the default run if, will be jump to if no matches expression. Sorry, we are out of, yeah, no, it shouldn't, it should not, wait. You have to add break, or else it'll run the default. So you have to add break. There you go. Huh, wait. It only ran once. It's weird. Yeah, you have to add break. And that means that after each case it won't so it'll go to, yeah, so you have to add break if you don't want the default to run. And if you don't, then it'll run. That was a problem. Okay, well, now I remember how to use switch at least. That's a good thing. Let's see, submit. Beats 5%, really? Wow. Why? It's probably the switch, isn't it? It's this rhythm so slow. It was technically pounds in length, but there's each very large. No, bro, my earlier response was even faster. So I guess that if you use if else all the time like this, it'll be faster for some reason. I'm guessing it's slow because of the switch that you have. I mean, the amount of calculations you have to do is pretty much the same, so I don't get why it's so slow. I don't get it. Yeah, I don't get why. For some reason, ifs are faster than switch. For some reason. This version is much faster. Why? To use the static data structure. That's what I did too in the switch. Instead of storing the expected closing tag in an array using the switch statement, to arrange the back into a stack, or push it up inside the stack. Reduces the number of constant time operations performed in the loop. Additionally, the updated version of the algorithm. I guess it's because switch. No, I don't see why it would be like, oh, maybe it's the console log. Well, if that's what it is, then submit. Okay, yeah, it's the console log. Can you delete this? No, you can't. Okay. It's the console log. So now it's essentially the same. Well, not essentially the same, but like it's much faster than before. So obviously when you have a console log, it'll be a lot fast. It'll be a lot slower. So because of the stack, there's more memory taken in here. You need less memory, I guess. So my version is actually better than this, although it's more complicated. But this one is much faster, but yeah, whatever. Whatevs. Okay, let's try another one. Wait, I'll add my last. Which is essentially just like a cleaner version. So wait, what? What happened? I see. So product of an array except self. Okay, I'll try this one. Okay, let's see. Given an integer array in numbers, return an array answer such that answer I is equal to the product of all the elements of nums except nums I. To the product of all the elements of num except nums I. Given an integer array numbers and array answer so that return array answer such that answer I is equal to the product of all the elements of nums except the product of all the elements. Okay, so product of any prefix or suffix of numbers is guaranteed to fit in a 32-bit integer. I'm not sure what that means. You must write an algorithm that runs in O of n time without using the division operation. Okay. Division operation. Write an algorithm that runs O of n time using the division operation. Okay. Huh. Okay. That could be, that's going to be a fun one, huh? So, not sure what this means though. So, a prefix sum is a technique used in computer science to pre-process an array of numbers so that we can efficiently answer range sum queries on the array. Given an array of n numbers, prefix sum of an element at index index I is the sum of all elements from the beginning of the array to and including the element at index 1 at index I. Given an array, the prefix sum of an element at index I. Okay. Preprocess an array of numbers so that we can efficiently range sum queries on the array. The prefix sum of the first element is simply the value of the first element itself. We can compute the prefix sum of the remaining elements by recursively adding the value at the current index. We can compute the prefix sum of the remaining element by recursively adding the value of the current index to the prefix sum of the previous index. Recursively adding the value of the current index to the prefix sum of the previous index. But here we're talking about product, not sum. Formally, we have an array A of n numbers. We can compute its prefix sum array P of length n as follows. Array of n numbers, okay. So basically, up to the element at index. Okay. So it's kind of the forgot what it's called, but like the big anyway, whatever. Once we have computed the prefix sum array P, we can answer range sum queries on the original array by simply computing the difference between the two prefix sums. prefix sum, we can reach of length n for I equals 1 to n minus 1 for I. Simply compute the difference. Specifically, the sum of all elements between indices I and j. The sum of all elements between indices I and j in the original array. Sum of all elements between indices I and j. What? I and j plus I1. Original array is equal to pj and pi minus 1, where pi minus 1 is prefix sum is element of the index. Right. Is equal to pj. Okay. Okay, so it's some sort of recursive thing. Some sort of recursive thing. So let's say we start with answer, which is an empty array, which will contain all the prefix sums of the numbers in the nums array. Answer. Okay. Okay, so now we have to do something here. Prefix sum, product of self. Products of self. So basically what we have to do, if we explain it into, first I need to understand what this means. Products of any prefix or suffix of nums is guaranteed to fit in of nums, the prefix or suffix to fit in a. What does that mean? I don't know what that means. If nums is an array of numbers, what does this mean? This means that for the given array nums of integers, the product of any contiguous, is that how you pronounce that? Contiguous. Sharing common border, touching, contiguous. Is that how you say it? Contiguous. The product of any contiguous subarray that starts at the beginning of the array prefix and ends at the end of the array suffix. Contiguous subarray that starts product of any contiguous starts beginning end of the array, so it will not exceed the maximum value of a 32-bit integer. In other words, if we take any contiguous, I already forgot. Contiguous, exactly. Contiguous, in other words, if we take any contiguous subarray of nums, okay, starting from the first element and multiply all its elements together, the result will not be greater than the maximum value of a 32-bit integer, which is 231 to the 31st power minus 1, or approximately 2.1 billion. Similarly, if we take any contiguous subarray of nums ending at the last element and multiply all its elements together, the result will also not be greater than the maximum value of a 32-bit integer. Okay, I already forgot what bit integers are. Maybe I should watch a video about that. This property can be used in certain algorithms and problems that involve computing. Wait, what's going on? What is going on? Okay, my thing froze for a second. So I was saying that the result will also not be greater than the maximum value of 32-bit integer of a value of a 32-bit integer. This property can be useful in certain algorithms and problems that can involve computing prefixes and suffixes of arrays, as it provides a guarantee that the intermediate products will not overflow at 32-bit integers. For example, it can be used efficiently. To efficiently compute the product of all subarrays of nums in O of n time complexity by using two prefix arrays to compute the product of each subarray. What? That starts at the beginning of the array and ends at the given index. And if suffix array to compute the product of each subarray that ends at the end, starts at a given index. Huh. Well, number of 1 bits. Yeah, I know what bits are, but I don't know. So, what are bit integers? I had a video that explained it. Forgot what it is. What are they? Okay, I'll just and bit integers, type integers, data type that has fixed size in terms of number of bits used to present the integer. The most common bit integer size. Okay. The size of the bit integer determines the range of integer values can be represented in amount of money. For example, can be presented values between. Yeah. Okay. So the choice of bit integer size depends on the program. Smaller bits you can say memory and be more efficient in certain contexts, but others can be more wider range of integer values require more money, more memory. Start counting bitwise operations. When we talk about it is important to clarify whether they are signed or unsigned by default or typically assumed to be signed, which means that you can present both positive and negative integers that range sign or is possible to present integers. But like use signedness of a 32-bit integer and perform operation conversation versions can result in negative values or flow. Okay. Okay. Is equal to product. So guaranteed fit in a integer suffix. So okay. I see. Oh, I see. So it's probably going to be like the suffix or and plus the prefix given an index, and then you add them two together. You get the answer, right? But how do you calculate that? So I'm guessing that you'd have to create two functions, one that calculates the prefix and one that calculates the suffix. Okay. So I'm guessing that you need two functions. You calculate the prefix and suffix and then add them together. Is equal to the product of all the elements of a num except you must write an algorithm that runs in O of n time and without using the division operation. Okay. So that's what it is, man. Like, it has to be it. Prefix. That has to be it. So my guess is that. So yeah, that's what it would be in my head. So a for loop that includes the function that calculates the prefix and the suffix. And you add them together. You push that into the answer array. You do that for every num in the nums array, and that's it. Now, what is the function of the prefix and suffix? It has to be recursion. Pretty sure that's what it would be, right? Recursion. So let's create a function. Prefix that takes in an index. No, it takes in an array and an index. Right? And then prefix. So basically that means prefix. It'll start at the index 0 and it'll end at the index given in the arguments. And then you want to do the sum of all those numbers combined. And so how do you do that? Basically you do, I know it's some sort of recursion function. So let's see. Times index times 0. So it would be something like prefix, return something like return prefix times, prefix of nums index times prefix nums index minus 1. Something like that. Right? Isn't that what it is? So let's say we take in an array that is, let's say the array is 2 and 5 and 4. 2 and 4. So you put that into here and you put the index as 2, let's say. No, as 1, sorry. And so that would give us prefix of this. Wait. No, it's supposed to be nums index times prefix. Right, exactly. That's what it is. That's exactly what it is. So in this case, you'd have 1 goes here, goes here. One of the nums would be 4, so that would be 4. So you'd get 4 times prefix of 1 minus 1 is 0, prefix, and then you go here, 0, nums of 0 is, you forgot the base case, which would be if the index is invalid. No, if index is smaller than 0, return. What do we return here? What do we return? 1. Return 1, 0, because here it would be 0 times prefix of a minus 1, and that would give us, that should be 0 or 1. This should be 1, right? It should be 1, I think, right? Return 1, right? Okay, that makes sense. And so that would give us, that would give us 4 times 1, no, times 0, sorry. And then 4 times 0 equals 0. That's it. That's all it is. That's all it is. And then if you do function suffix nums index, you do if index, again, if index, it has to be plus 1 this time, right? Because we're doing, is it like overheating or something? Probably. Whatever. So suffix, it's from an index to the end, right? So from an index to the end, so it would be index, if index is greater than, no. Yeah. If index is greater than nums length, then return, nums length or nums length plus 1, I think. So let's see. So in this case, if it's greater than length, no, if it's greater than what? If it's greater than length plus minus 1, right? Length minus 1, I believe. If it's greater than length minus 1, right? because the last index is length minus 1. The last index is length minus 1. Right. So, if that's the case, you return 1. You return 1, right? Because that's the absorbent factor in multiplication. Nums, so it's essentially the same thing. So nums index times suffix nums index plus 1, right? Exactly, plus 1 until you get to the last. So let's say the subarray is this thing. We should get the same thing, right? So here we would get nums index here we would get, let's say the index is 0, right? 0. So it's 0. Okay, that won't be an O of n if I understand correctly. That will probably not be an O of n. But I think that it's logically sound what I'm doing right now. But let's say for suffix the index is 0. What happens then? You get nums. The length is 2. Minus 1 is 1. So wait, index 2. Yeah, okay. It's cool. So it's index 0 would be 2 times suffix index nums index plus 1. Plus 1, which would be 1. In this case, it would go into here. Nums of 1, index 1 of nums is 4 times index plus 1. So again, we get wait, is that? No, it's fine. Yeah, 0 and then plus 1, 1, 4, 4, and then here it'll be 5. No, it'll be 2. Correct? Correct. It'll be 2. And what happens if index is greater than the length minus 1? It returns 1, so that would be 1. And so that would be 2 times 4, which gives us 8. Is that correct? It is correct. Is that what I got the last time? I don't even remember. But essentially, it should give us the same thing, the 8 here. So here you'd have 1, and then you'd have in nums, index 1 of nums is 2 times, no, it does not. It does not. Wait. No, wait. 2, right. No, it's 4. What am I doing? 1, index 1 of num is 4 and then minus 1, it's 0. It's 0 times index minus 1, which is not in the array, so it's 1. What am I missing? Wait, what am I missing? No. 1, 4, 0, 2. I don't know why I said 0. But here would be 0, because 1 minus 1 is 0. And then here, 0 is equal to 2. And then index minus 1 is 1. So 2 times 1, which gives us 8 as well. Okay, so our functions are working. And so we would have a for loop that goes through the numbers. Starts with 0. And then we get I nums length nums nums wait, what am I doing? For I 0 blah 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 blah. Okay. Okay. Answer. Let answer. Answer. So that's gonna be messy if I do that, but let's just do let p equal. Wait, I gotta put the functions in. Here. So let. Can I? I'll just put them inside, because why not? Right, and then let p equal prefix. So so it's inclusive or not? No, it's exclusive. It's exclusive. So prefix nums index minus 1, correct? Right, minus 1, and then let s be equal to suffix nums index plus 1. Right, index plus 1. So now, if the index is 0, this would give us 1. Wait, that's a problem. Wait a second. No, yeah, it's fine. It's supposed to give us 1. Right? Wait. Return array, ensure that such that answer I is equal to probably of all elements. Okay, yeah. So it's supposed to give us 1. And then you do answer Wait. Answer I is equal to P times S, right? I think so. And then here you return answer, right? I'm very skeptical, but let's see. No thanks. Index is not defined. Okay. Forgot to change that. It works. Wow. But I don't think this is O of n at all. I don't think so, right? I don't think so. I don't think so. I think it's O of n squared. Because of the for loop, inside the for loop you have these recursive things. As follows. Functions to helper functions, prefix, suffix, which are recursive, where n is the length of the input array, nums. For each element in the input array, the function calls prefix and suffix. Yeah, I know. I'll submit it and see what happens. So this is complete nonsense. Yeah, so I think that my thing works, but it's probably too much. Again, it's always the same pattern with me. It's always too much. Too complicated, too much, you know. Yeah, it's always too much. Yeah, I mean, for each element in the imp array, the function calls prefix suffix, which takes O of n time each. Therefore, the loop over the imp array takes O of n. For each, here's n is imp array nums, right? For each element in the input array, the function calls prefix, which takes O n time each. Therefore, the loop over the imp array takes O of n time. Within the loop, the function performs a constant number of operations, namely the assignment. Therefore, the operation is within the loop, the function performs a constant number of operations, namely putting all this together, overall complexity of functions performs so much elements. Each element in the array function calls, which takes yeah. So my answer wasn't going to be correct anyway, but yeah. I need to go to the bathroom, so I'll be back. Alright, so my solution logically works, but it's in O of n squared. So I need to find a way to make it O of n. Now, I doubt that I'll be able to find that solution within the next few minutes, but I'll try. And if I can't, I'll simply look at the answer and I'll study it. But let's try to find something. So, okay. Okay, so basically, we have the problem is that we have recursion within a for loop. And usually the solution to lower the time complexity is to create some sort of hash map or hash table, which can be accomplished with a simple map. Now, I'm not sure how I could implement that. Again, if in a few minutes, if I can't find anything, I'll simply look at the answer. But let me think. I think we could get rid of the for loop somehow. But I don't know. I don't know. I don't think so. I don't think we can. We have to wait a second. Maybe if no, that doesn't work. Wait. So I'll ask the AI to give me a hint. Would be to try to calculate both the prefix and suffix products of the array in a single pass through the array instead of using recursive functions to calculate them separately for each element. Interesting. So I was kind of right. You don't need the for loop. Okay. So let's see. Let's see. How can I do this? No. Yes. Yes. Okay. 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 So it's not recursion. Or maybe it is, but it's not the functions that I built here. Okay. Um, let's see. Iteration. I actually don't know, man. I don't know. Let's think about this. Prefix, suffix, prefix, suffix. All right, so I'm trying to figure out what the how can I make this algorithm be have a time complexity of O of n instead of O of n squared. And now I'm being told by the AI that I do need a for loop. I need to change how I do my prefix and suffix functions. And yeah, that's what I know so far. I'll try to get more hints. Um, um, only yes or no. Will I have to use recursion any for any part? No. Okay. Okay. So I don't need recursion. Um. One hint to achieve an O of n solution would be to try to calculate both the prefix and suffix products of the array in a single pass through the array instead of using recursive functions to calculate them separately for each element. We try to calculate both the prefix suffix products of the array in a single pass through the array instead of using recursive functions. Okay. So basically, you would have to iterate through each. I think. Is everything. No. Wait. So basically. Okay, let's ask. Yes. Does the for loop iterate? Oh shit, I'm stupid. Okay. That was not a yes or no question, but yeah. Okay. So basically, my issue is here. I cannot use recursion. I can't. I'll keep that for documentation's sake. Code. Code. So that's the wrong, right? Right. So that's the wrong answer. So we need something else here. How do we calculate the prefix? Suffix without recursion. Without recursion. It has to be using a hash map or hash table or a map or something. How do we do this? How do we do this? For each element. Okay, so use two arrays. Okay, but how do you calculate it? Calculate both the prefix box of the array in a single pass. You choose arrays to keep track of the prefix box of each element. Okay, but how do you calculate it for I? Bro, I have no clue. Hash map. Hash map. How? You still have to calculate that. But I don't know. Through the array. To do this, you can create two arrays. One to keep track of the prefix box or not. Array to the nums array twice. Once you create prefix box, suffix box. First array, you can calculate the prefix, store them in a prefix array. Wait. Bro, what? I do the numbers around one more time, calculate the prefix, store in a prefix array. But how? Prefix sum. Um, what? Wait. What? Prefix? Isn't that wait. What is going on? 1, 0, 1 times nums. Yo, what? My brain's not working right now. Prefix nums. What's going on? What is going on? Prefix I minus 1. So here would be 1. Oh my goodness, what is going on? So it'd be 1, which that doesn't even exist. It would be undefined or what? Null. Prefix. Undefined, exactly. So it's undefined. Prefix I minus 1 would be 0, which means it's 1. Prefix. Right. It is 1. It is 1. I minus 1 times nums I minus 1. Prefix I minus 1 nums I minus 1. 1 undefined equal I minus 1, which is 0, 1 times nums I minus 1, which would be 1. What if it's 5? Would be, it would be 5 would be 1. Jesus Christ. We're calculating the prefix here. So 1 times, okay, yeah, it's supposed to be 5. What about 2? 2 I 1. What is going on? 2 which is 1, which is 1. We've established it's 5, right? So console log prefix 5. Wait. It's essentially, wow. So you're storing the value externally and reusing it on the next loop, on the next iteration in the for loop. So it's kind of, no, it's not recursion, but it achieves the same thing. It's just that you're kind of like outsourcing the memory and into an array, and then the calculation is done with the for loop with assistance from the array. Huh. Wow. Wow. That's pretty smart, isn't it? Wow. I don't know. Wow. So using wow. Nums 5 2 5 times 2 1 2 5 10. I'll just write it out again. Accept self as nums, and then you have prefix. You didn't understand what I meant, but prefix I is equal to a prefix wait. I'm trying to see how to make the array work, make the algorithm work if we consider I into the prefix and the suffix. Change initial algorithm if we include I into there. That's stupid. That makes no sense. That makes no sense. What I'm trying to. That makes no sense. Yeah, that makes no sense. Yeah, I mean, prefix -1. So, I mean, recursive function next to external array for loop doesn't need to retain memory I'm trying to understand how the for loops work. Yes, that's correct. The recursive functions for previous would achieve the same result as the for loops, but we use more memory due to rather maintain the call stack. Right. By using arrays to store the prefix suffix functions, we are able to achieve the same result as the recursive functions without incurring the overhead of the call stack. This leads to a more memory efficient algorithm, which is an important consideration for large input sizes. In general, recursive functions are useful when the problem can be broken down into smaller subproblems that are similar in nature. When there is a base case that can be handled directly. However, in cases where recursion would lead to excessive memory usage, it's often more efficient to use an iterative approach. Is iterative. I'm trying to understand like the prefix and then use those products to go to the final answer. Is are recursive functions okay? No, let's talk about so when building when writing an iterative alternative to a recursive functions with the help of a for loop, do we often initialize, do we always initialize the first, do we always have some sort of data structure where we will store the result of every loop, or not necessarily, depends on the specific problem we're trying to solve. In some cases, maybe to additional variables to the loops without need to store image. For example, we've been discussing we use two arrays prefixes to store intermediate results to the previous subtract. Some other point may only need to update a singular variable or array as you iterate through the loops without needing to store results separately. I think I see it now. I think I get it now. In general, the key idea behind an iterative is that you were breaking down problems, smart subproblems, something one by one without the overhead of recursion. Okay. How we store and data will depend on the specific problem. Okay. So I'm trying to think here. When using a for loop in an iterative solution, do we often see things like I minus 1 or I plus 1 to access past results from past loop results or executions? Isn't that a distinctive characteristic of an iterative for loop that is replacing a recursive function? Isn't that it's not simply distinct, but it is a common technique. In many cases, it involves building a solution best outside, and it's often helpful to refer as possible the current result in a way to use an index like for loop, keep track of where use like past results. So what am I doing? Because all I'm going to do cost solution break then find a smaller recursive algorithm where we are in the computation we use like mostly the key is build up something break down the smaller problems. Yeah, I mean it's the same thing as it's doing the same thing as a is it doing the same thing? It's like I'm trying to think. I'm trying to understand this deeply. I mean, so is it doing the same thing? Split the input. Okay, so now we're talking about divide and conquer approach. And that's something that I've never really studied before. You can split the input array into two halves. Recursively compute the prefix and suffix approach for each half. Once we have the prefix and suffix products for each half, we can use them to compute the final answer for the entire array. We can split the input array into two halves. Recursively compute the prefix products for each half. Once you have the prefix suffix products for each half, we can use them to compute the final answer for the entire array. I don't really get it. Once we have the prefix and suffix product for each half, we can use them to compute the final answer for the entire array. Wait, what? What the hell? Compute products if start equals end. What the hell? Way to divide and conquer. Okay, you know what? I'll just watch a video about divide and conquer because conquer. What? Okay, here.
So let's imagine that you have $100,000 in student loan debt. In this world, for some of us, this might not be far from the truth. And as is common with student loans, your total debt is the sum total of multiple individual loans. Now, unless you're already rich, it's probably not possible for you to pay off the entirety of this debt in one payment. So the usual approach would be to tackle the loans individually, gradually paying each loan off. In other words, once we've divided the 100K debt into individual loans, we can tackle them in isolation from one another. So over time, we'll pay off each individual loan, which will eventually come together to completely pay off our overall debt of $100,000. And this is the divide and conquer algorithm. And that's pretty much all there is to it. We first divide the problem into subproblems of the same related type. So in this case, each subproblem is subtracting debt, and then we conquer, where the combined solutions come together to form the solution to the overall problem. So let's apply this to something more technical. We'll use a sorting algorithm called merge sort as an example. We're presented with an array that we want to sort. And the first thing that we do is divide the array down to individual arrays of size 1. Now, an array of size 1 is technically sorted because, of course, there's only one element. So within the conquer portion of the algorithm, we will merge the sorted arrays. And we do this by making use of another algorithm or pattern of array that we want to sort. And the first thing that we do is divide the array down to individual arrays of size 1. Now, an array of size 1 is technically sorted because, of course, there's only one element. So within the conquer portion of the algorithm, we will merge the sorted arrays. And we do this by making use of another algorithm or pattern where we make use of 2 pointers. And if you aren't familiar with the 2 pointers pattern, I have videos explaining this that you can access by following the link above. So if we have 2 sorted arrays, we'll start both pointers at index 0 for each array. We then compare the two values referenced by the pointers. 1 is less than 2, so we'll take that value first, and then we increment the pointer for the right array. 2 is less than 3, so we take that value and then increment the pointer. 3 is less than 4, so we take that value, and at this point, the pointer on this side can't increment any further. So we then just append the rest of what is pointed to by the other pointer. We're then left with a sorted array. So back to our merge sort visualization. Once we've reached the end of the conquer portion of our algorithm, we're left with a sorted array. And this is divide and conquer. If you want to learn more about merge sort, including coding examples and its time and space complexity, I have other videos on the topic that you can access by clicking the link above.
Hello and welcome to Winslow Academy. So in this short video we're going to discuss the divide and conquer paradigm, which is an algorithm design paradigm within computer science, but you can also use this in a general thought process whenever you are doing something complex outside of, for example, coding or designing algorithms. But basically what divide and conquer is a way that you divide a larger problem into different subproblems such that you can solve these problems and then combine the solution into a final stage where you actually have gotten from a complex stage down to a bottom stage and back up to the complex stage with a
Hey, what's up everybody? In this section of this course, we're going to go over the 2 pointers pattern. The 2 pointers pattern is basically exactly what it sounds like. We're going to make use of 2 pointers to keep track of 2 data points simultaneously, which is going to level up our ability to write more efficient algorithms. We'll start with a simple example that will present you all with a clear picture of what I mean when I say that we can keep track of 2 data points simultaneously. To better illustrate this technique, I've chosen a problem that's not in our LeetCode patterns list for this first example, but don't worry. The problem examples following this first one will be part of the LeetCode patterns list. So the problem that we want to take into consideration for this first problem is this one here. We're asked to find 2 numbers in an ascending ordered array of numbers that add up to a target value. The array is guaranteed to have exactly one solution. That is, we can rest assured that there are exactly 2 numbers within the array that add up to the target value. And by exactly, I mean exactly, no more, no less. And for some strange reason, the array is 1 index, so we'll need to keep that in mind as we work through this problem as well. So let's imagine that we have an array that looks like this, and a target that is 22. And we want to find the 2 numbers in this array that add up to the value 22, the target. The naive solution to solving this problem would be to iterate through this input array, and for every index of the array, check every other index's value to see if the 2 values combined equal our target. As you can see, this solution isn't very efficient because we are unnecessarily iterating through elements that we've already seen before. That is, when we're calculating all of the values in the array with this first value 2, we already see every other number in the array. So in theory, after that first round, we've already accessed the 2 values that result in 22, those values being 7 and 15. But even so, we still won't realize that with this solution until our second trip around when we calculate all of the values in the array with the second value 7. Now let's try to visualize the more efficient solution using the 2 pointers pattern. So remember that 2 pointers means exactly that. We're going to use 2 pointers to keep track of 2 separate values simultaneously. So let's imagine that we have the same array and the same target 22. This time we'll place a pointer at both ends of the array, hence 2 pointers. Following that, we simply add the value at the first pointer and the value at the second pointer together to see if they add up to our target. If they don't, we simply check to see which pointer we should move inward by taking into account whether or not our calculated value is less than or greater than our target value. So the important point here is that our array is an ascending ordered array. That means that the values at the end of the array are going to be larger than the values at the beginning. So if our calculated value is greater than our target, that means that we need to decrease the size of our calculated value. We do that by moving our rightmost pointer to the left because remember, the further right we go, the larger the numbers become. So we want to use a smaller number for our addition because our result was larger than the target. Same for if the result wasn't large enough. We'd move our smaller number pointer on the left to the right to increase the value of our addition. And as you can see, this is a much more efficient way to solve this problem. Now let's get into writing some code. For this pattern, and most likely for the rest of the patterns in this course, we're going to be using Python. But don't worry, if you're familiar with any other programming language at all, you won't have a problem following along with this course. So let's first briefly go over how to install Python. The installation process for Python starts at Python's website here, which I will also link in the description. So to start, you'll just want to go to this Downloads tab and then download Python 3 for your operating system. After the into this naive.py file, and we'll define a method called toSum2, and we'll do nums and target, and we'll just do for I in range length of nums. So we're going to iterate through our nums array, and for every iteration of our nums array, we're also going to iterate through that same array starting from whatever index that we're on. So for j in range, and this range is going to start at our current index plus 1, and it's going to end at
Wait. That's interesting. So what if to calculate the one way to do this would be to use a divide and conquer approach. We split the input array into two halves. Compute the prefix suffix row for each half. Once we have the prefix and suffix for each half, we can use them to compute the final answer for the entire array. Products of self function compute products. No, I'm sorry, and if return 1 1. Okay. Let me rewrite this first. Swan. Jeez. Suffix 0. Gives you the last index. So then you initialize the first answer of yeah, because the thing is, how can I explain this? Basically, something that a result, an answer that can be found recursively is essentially means that each answer will depend on the previous one. And so the only independent answer, let's say, is the first one. So here, the first one would be 1, right? Yeah. Yeah, it would be 1. No, it wouldn't be 1. Prefix. Why isn't it not 1? It is 1. What am I talking about? But it's not, though, because, well, yes, it is. But why? Without itself. It has to be 1, right? Why? Because we're not including the index itself. So it would be 5 and then 5, 2, 10. Yeah, it is 1. I don't know what I'm talking about. 1 in here. You start at 1. Why? Why do you start at 1 and not 0 here? Well, because why is it 1? Why? Because we've already established 0, right? Right. And now that initializes everything. And then it's like you're iterating through an array, but as you're iterating it, you're making it. You're making it as you're iterating through it. That's interesting. That's interesting. That's interesting. That's interesting. So I would be I would be nums length minus 2. Minus 2, right? Yeah. Is equal to nums length minus minus 2. And then I is greater than 0, right? No, greater than minus 1. Greater than minus 1. Greater than minus 1. Greater than minus 1. I'm pretty sure that's what it is, right? And then I will be subtracted by 1, and then suffix I will be equal to suffix I plus 1 times nums. That's the part I don't get. Nums. see. Wait, no, I don't. Two. Jesus Christ. Do. Two. One. Jesus Christ, bro. So oh, that makes sense. Makes sense. Yeah, I mean, it's kind of hard to wrap your head around that, but especially when, yeah. But I get it now. I get it now. Jesus Christ. Okay. So that should work. And then you do answer a final for loop with O nums length. Oops. I is smaller than nums length. I so answer I is equal to answer I is equal to prefix I times suffix I. That's it. And then you just return answer. Return answer. I'm missing something, I think I am. No, I'm not. Jeez. Okay. It's 55. Again, I mean, it's weird. It's weird. I don't get why. It's so natural for me to think about nested for loops and O of n squared solutions. So yeah. Yeah, so essentially the same thing as what I did. So I'm trying to understand this now. Yes, it's possible to create a recursive algorithm that achieves the same thing as the array algorithm. Blah 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 blah. We can split the input array into two halves and recursively compute prefix suffix products for each half. If you're watching this right now, you're a crazy person, but I appreciate you watching. We can split the input array into two halves, recursively compute the prefix suffix products for each half. Once we have the prefix and suffix products for each half, we can use them to compute the final answer for the entire array. Here's some simple code to demonstrate this approach. Yeah, I mean, for each half. But that's not enough. You need both, don't you? Okay, let's see. I'm trying to understand this. It still has, because each element of the array is only once in the computation. Prefix of the product, however, the space is higher than the iterative approach because it requires recursion and additional function call overhead. Yeah, okay. Trying to understand it though. I want to see if does it actually run. It doesn't work. You stupid AI. It doesn't even work. Your algorithm doesn't work. Well, it just doesn't work. What do you want me to say? I mean, it just does not work. I don't know why it just doesn't work. Output is outputs. You're right, apologies for the misapprehension. The issue with the code is that when computing the prefix box we have, we need to initialize prefix to 1 instead of correct code. Here's the corrected code. I doubt that'll work. I doubt that'll work. Does not work, buddy. Still doesn't work. I don't think that it's possible what you're asking for. You know who I call when I need help? This guy. This guy. Call this guy. So let's take the initial algorithm that we had. Wait. Is this an iterative or recursive function? It's iterative. Okay. Can you rewrite this algorithm to so that it achieves the same thing but in a recursive way, and with a time complexity of O of n or less. This guy's not going to tell me. For some reason, when I ask this to ChatGPT, he thinks that, well, it thinks that it's possible when it's not. But if this guy tells me it is possible, then it is possible. We can write this using recursion in a possible way. I have to complete recursion call for empty array. Let insert new array nums line to create empty array. Helper call helper function with what return answer, return the final answer array. Wait a second. So, yes, this is the one. Simplified version, the clean version. Why is it like that? Where is it? Java, 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 JavaScript. Okay. Product, except self, blah, blah, blah. Let suffix. Yeah. Oh, that's really good. So, I spent a lot of time on this problem, but it's because I know that if I understand that problem like very deeply, I'll be a lot better when it comes back in a different form. When this kind of problem comes back in a different form, I know that I'll be a lot faster because I will understand what it's, what is at stake and what I'm trying to do and how I can do it. Because now I've found new ways to accomplish things that I would do otherwise before in a less efficient way, but now I know new ways to do it in a more efficient way. Okay, so now let's see. Let's see. Let's see if this actually works. Run. It works. It does work. So let's submit it. Okay, so it's worse. No, it's not. It's slightly better, but it takes a lot of memory. A lot of memory. And it's probably a lot more complicated. But let's see what it is. Because I think that if I understand that problem, I will be in a better position to understand other problems. What is time complexity of this? Let's see if this guy is not lost. Okay, so is that a recursive or iterative algorithm? Function calls itself should be the base case. Yeah, Bing is a lot better than this guy. When it comes to like complicated stuff, I think. But I haven't used this I haven't used Bing as much, so I'm not sure how good it is, but I think I'll start using it more because it seems like it's better when things get a bit complicated. So let's see. Let's try to understand this. Okay. Create an empty array. Okay. Helper function. The helper function is called inside itself return answer. Okay, so everything is happening inside this helper function. So let's see. If index is equal to num's length, return 1. Right, as the rightmost product. Rightmost product. If we reach the end of the array, return 1 as the rightmost product. If we reach the end of the array, it's the rightmost product. Is the rightmost product plus 1. Okay, we get that. I mean, it's not rocket science, as they say, right? Okay, so right product. Helper nums index 1. Nums. So you have the array index product and answer. Okay. And the answer has been initialized as an empty array with length of nums. Product 1. Index. Okay. Okay. Index 0 product. Yeah. The prefix of. So I'm not sure what product is here. But I guess it's like the prefix, right? I'm guessing it's the prefix. Recursive call. Get the product of all elements to the right of the current index. Get the product of all elements to the right of the current index. Get the product of all elements to the right of the get the product of all elements to the right of the current index. Okay. So index product, right product. Yeah, that's where like my brain is like not following. When it becomes recursive, like my brain for some reason like it stops following. Rewrite it using yeah. So you see, like, that's something that GPT would have understood. Is it would have understood? Yeah, he would have understood. Can you please verify because you want me? Explain logic in a different way. No, I mean, or maybe it's actually very smart and it actually wants me to clarify because it's actually not that clear what I want. Exactly. So actually, I think it's actually better so far. Okay, I can use different algorithm. Function index prefix product. Yeah, exactly. So it is a prefix. Suffixed. Suffix and a prefix. Prefix. Suffix. So it takes in the index and the prefix. Okay, so then it sets the suffix. Wait, the suffix. Jeez, wait. Prefix. The suffix with the array, the index, plus 1. Plus 1. Plus 1. Prefix times num's index. Okay. Well, I don't think that's the suffix. Get the prefix of all elements to the right of the current index. Wait, I don't think that's the correct. Wait. And now yeah. Suffix times it takes in all the prefix of left and right prefix. Yeah, it takes in the first index and then calculates recursively everything on the right. Right? Is that what it is? Answer and then prefix, suffix, answer index. Jesus Christ, man. I know there's a bunch of nerds that would get this in half a second. And I've been on this problem for like an hour or more. Yeah. Whatever. Update the answer array with the prefix of self of left and right. Answer array with the prefix of left and right. Yeah, it just keeps going to the end until you get 1. And then it returns answer, prefix, suffix. It returns index. It returns the suffix, which is everything on the right, times the current index number, which is that's weird. No, okay, yeah. So here it's where you build the array here. So for each index, you get the prefix of that index times the suffix of everything on the right. The product of everything on the right. Right? Is that? Yeah. Yeah, man, this thing is incredibly, like, it's a mind. It's hard to understand. But I think I think I get it. It's hard to think about recursive functions.